In one of our previous lecture, we have seen that initial value problems of first order ODE may not have any solutions or even may have more than one solutions. In this lecture, we would see the conditions under which initial value problems for first order ODE has solution and under what condition the solution is unique. For this, in the previous lecture, we have introduced what is known as Lipschitz condition. This condition will play an important role in this existence and uniqueness of solution of initial value problem for first order ODE. Let us recall what is the definition of Lipschitz condition. Let f be a function on a domain D. The D is assumed to be a domain or a closed domain in the xy plane. By a domain we mean an open set in the xy plane, and by a closed domain we mean a closed set in the xy plane. By a closed set we mean that the set contains all its limit point. So here f is a two variable function. A function f is said to be satisfying Lipschitz condition in the domain D if there exists a constant m greater than 0 such that the modulus of the difference of fx comma y1 and fx comma y2 is less than m times the modulus of the difference of y1 and y2. For every x comma y1 and x comma y2 belonging to D, the constant m is called the Lipschitz constant. We have also noted in our previous lecture that if f satisfies Lipschitz condition with respect to the variable y, that is the second variable in the domain D, then for each fixed x, the resulting function y is a continuous function. The resulting function of y is a continuous function of with respect to y, that is the second variable in the domain D. Also recall that we have seen that continuity with respect to second variable does not imply Lipschitz condition satisfied with respect to second variable. For that, we had considered an example, namely fxy is equal to square root of modulus of y. So here the function f on x comma y is a continuous function for all values of y. But f does not satisfy Lipschitz condition for any region that includes y is equal to 0. Because if we select, for example, y1 is equal to 0 and y2 greater than 0, then we have that the modulus of the difference of f of x comma y1 and f of x comma y2 divided by the modulus of the difference of y1 and y2 is equal to square root of y2 divided by modulus of y2, because here y1 is 0, and this is equal to 1 by square root of y2, which can be made as large as we want by making y2 smaller. So the Lipschitz condition, we know that requires this quotient to be bounded by a fixed constant k. But since we can make this quotient to be as large as we wish by choosing y2 to be small enough, so this particular function does not satisfy Lipschitz condition. So what we have seen till now is that a given function which satisfies Lipschitz condition with respect to second variable, then it will be continuous with respect to the second variable. But the continuity with respect to the second variable does not imply Lipschitz condition satisfied with respect to the second variable. But we will see now a sufficient condition which implies Lipschitz condition with respect to second variable is satisfied. Continuity is not a sufficient condition. It does not imply Lipschitz condition with respect to second variable. The condition that will be sufficient is that in addition to the continuity with respect to second variable, we need to assume that the partial derivative of f with respect to y exists and is bounded. So here is the sufficient condition. If f is a function on two variables, and f is defined on some domain D in the xy plane such that the partial derivative of f with respect to y exists and is bounded for all points in the domain, then f satisfies Lipschitz condition with respect to second variable y in the domain D. And the Lipschitz constant here m is equal to LUB, where xy varying over D modulus of del f by del y of x comma y, its modulus, that quantity is the m. So with respect to this m, this definition of Lipschitz condition is satisfied. So it says that if the partial derivative of f with respect to y exists and is bounded in the domain, then the function f satisfies Lipschitz condition with respect to the second variable. We'll see the proof. The proof follows from mean value theorem for functions on two variables. So we can write f of x comma y1 minus f of x comma y2 is equal to, in bracket, y1 minus y2 bracket close del f by del y of x comma xi, where xi lies between y1 and y2. Then modulus of fx comma y1 minus fx comma y2 is equal to modulus of y1 minus y2 times the modulus of del f by del y evaluated at x comma xi, and this is less than modulus of y1 minus y2 times LUB, where xy vary over D modulus of del f by del y evaluated at x comma y. So here LUB stands for supremum. You must be familiar with this terminology. So if you write m instead of this LUB, then this is precisely the Lipschitz condition. So this says that f satisfies Lipschitz condition. So the sufficient condition is if the partial derivative of f with respect to the second variable y exists and is bounded for all points in the domain D, then f satisfies Lipschitz condition. We'll see an example now. If f of x comma y, where x and y is inside a rectangle, so modulus of x is less than a and modulus of y is less than b, this forms a rectangle, closed rectangle. So if f x comma y is defined to be equal to y square in the domain D, the domain D is that rectangle, then the partial derivative of f with respect to y is equal to 2y in the domain D, and this particular partial derivative is clearly bounded in the domain D. M is equal to LUB, where xy vary over D modulus of del f by del y evaluated at x comma y. This is equal to LUB of x comma y belonging to D modulus of 2y. And we know that here this modulus of 2y, its supremum or LUB, is 2b, because modulus of y is less than b. So the Lipschitz condition is satisfied with respect to this Lipschitz condition, m is equal to 2b. One can verify this Lipschitz condition directly also. We have seen in our previous lecture that a similar function we had shown that it is Lipschitz continuous or satisfies Lipschitz condition directly from the definition without using the partial derivative of f with respect to y being bounded. So that you can apply here and see. In that method also, it turns out that m is equal to 2b. Note that the existence of bounded derivative is a sufficient condition. That means even if a function satisfies Lipschitz condition, that does not imply that the partial derivative of f will exist and will be bounded. Here is an example. The function f on two variables x, y on the domain D, where the domain D is rectangle, namely modulus of x less than or equal to a, modulus of y less than or equal to b. So function f x, y is defined to be equal to x times modulus of y on this domain. Here clearly you can see that the del f by del y does not exist for any point x, 0 in the domain, because modulus of y appear, and you know this modulus of y is not differentiable at the point 0. But the function f satisfies Lipschitz condition. We can calculate and check that. So modulus of f of x, y1 minus f of x, y2 is equal to modulus of x times modulus of y1 minus x times modulus of y2, and this is equal to modulus of x times modulus of y1 minus modulus of y2, which is less than or equal to modulus of x times modulus of y1 minus y2, which is less than or equal to a times modulus of y1 minus y2, because modulus of x is less than a. So we see from this that f satisfies Lipschitz condition. The Lipschitz constant here is a, but the partial derivative f with respect to y, that is the second variable, does not exist. So as I said before, the existence of bounded derivative fy is a sufficient condition for the Lipschitz condition to hold, but it is not necessary.